Not every function that you see will have two variables. What you're used to seeing are functions that look like this. There are two variables here, a y and an x. What you'll begin to see in Calc 3 are functions that look like this. There are three variables here, a z, a y, and an x. These will be more common when you get into the real world of 3D graphing. Now sometimes one of these variables will move while the other stays in place. In what you've been used to seeing with these kind, you'll take a derivative of a function y in terms of a function x. That means that the x is moving and the y is staying constant. Now look, on our 3D graph here, if you are told to do dy dx, what happens to the z? That's what we're going to talk about today. So when you're told to take a derivative, this is what you're used to. We're going to learn a special notation that looks like this. This is going to signify a partial derivative. Now, the partial derivative of a function z in terms of now let's use our example from before, z equals y plus x plus 2. So now we can have a partial of z in terms of y, or we can have a partial of z in terms of x. And these two are what we're going to focus on in this module. Now, when you have a partial x, that means that the x is moving, just like you had here. So when the x is moving, the x acts as a variable, and any other variables that will be in this function here, those will all act as a constant. So if we took the partial of z, and then we have this as our z in terms of x, this y will act as a constant, because the y is not moving, just like the 2 does not move. So the y and the 2, now the derivative of a constant is always 0, right? So the derivative of 2 is 0, and the derivative of y will be 0. So those will both 0 out. Now what's the derivative in terms of x of x? That's just 1. So this partial, the answer is 1. Let's try another example. If we have z equals x squared plus 2y squared plus 3, and we're looking again for our partial of z in terms of x, the x is our variable. So we'll get 2x, y is a constant, so y acts just like a regular number, so these both will go to 0, and 2x is our answer. Now the inverse of this is true as well. We can take a partial of z in terms of y, and here, so I'll rewrite it again over here. Here's our z. There's our z equation. This just signifies the equation in terms of y. So this time the x is a constant, 3 is still a constant, and we'll get 4y as our answer. Let's try one more example. So we'll get x to the third plus 6y squared plus 12xy plus 3. And we'll find our partial of z in terms of x. Alright, what's the derivative of x to the third? 3x squared, 6y squared. There are no x's in this set part of our equation at all. So that's a constant. No x's in here, that's a constant. But here's an x. If there was no y here, so let's just get rid of this y for a second. We'll act like it isn't there. If it was just 12x, the answer here would be 12. But there's a y. Now 12 is a constant, and y is a constant. So the derivative here is 12y, since these both act as constants. It can go the same way if we did it this, but there are no y's here, so that goes away. This has y's, that becomes 12y. Okay, no constants here again, so that's canceled out. Now here we have 12xy. The 12 and the x are both going to be constants here. So we'll have plus 12x. that is the basic of partial derivatives. You can continue on to this module to solve the rest of these equations, and if you have any questions, feel free to ask.